Good evening and welcome to this video for the 2020 Level 3 complex numbers for Level 3 calculus. So for question 1, if s equals to 2 plus 3i and t equals to 3 plus ki, find the value of k if s times of t equals to 21 minus I. Alright, for this question, we're just going to multiply s and t together. So if 2 plus 3i multiplied by 3 plus ki, so that's st. So we would just expand this like we would expand any two brackets. So we would just multiply everything together. So 2 times 3 is 6. 2 times ki is positive 2ki. 3i times 3 is plus 9i. And 3i times ki is 3ki squared. I squared is negative 1, so minus 3k. So now we have our imaginary parts and our real parts which we can distinguish. So st equals to 6 minus 3k. Plus 2k plus 9i. So now we know that the real part is equal to the real part and the imaginary part is equal to the imaginary part. So the real part 6 minus 3k must be equal to the real part, which is 21. So therefore we should see that negative 3k is equal to 15 and therefore k equals to negative 5. We can use this to check that our imaginary part is also equal to negative 1. So 2 times negative 5 is negative 10, plus 9 is negative 1. So it is indeed negative 5. And this should just be an achieve level question. Question B, find the values of r such as the equation x squared plus 4rx plus r has only one solution. So this is actually a pretty typical just level 2 question, to be honest, since this is just our standard b squared minus 4ac, our discriminant equals to our discriminant equals to 0, since there's only one solution. So in this case, our discriminant equals to 0, so b squared minus 4ac equals to 0. So if we have 16r squared, that's 4r squared, so 4r whole thing squared equals to 16r squared minus 4 times of a, which is 1, times c, which is r, equals to 0. 16r squared minus 4r equals to 0. If we factor out r, we'll have 16r minus 4 equals to 0. So therefore, r equals to 0, or r equals to 1 over 4. That's our final answer for this question, and this should be just another achieve question there. Question C, solve the following equation for x in terms of g. 2 root x minus 5 equals to square root of 4x minus g. So for this question, it's best that we separate the square roots, which in this case it's already done. So we want to have one square root on one side and the other square root on the other side. So in this case we do have that. So we have 2 root x minus 5 on the left hand side, and we have square root of 4x minus g on the right hand side. So we can immediately just square both sides. So we can say that 2 root x minus 5 whole squared, that equals to square root of 4x minus g whole squared. So therefore, if we square the left hand side, we'll have 2 times 2 is 4, root x times root x is just x, so that's 4x. Negative 5 times negative 5 is plus 25, and we have negative 5 times 2 is negative 10, so we do it twice, so that's negative 20 root x, and that equals to 4x minus 9. 4x and 4x will cancel each other out. We can move the 9 to the other side, so we have 34 equals to 20 root x. Yeah, we have that's what we have. So now we have to square both sides again. Okay. Oh, sorry, it's not 9. It's g. My bad. That's g. My bad. That's a g. Poor handwriting. Okay. So 25 plus g. Apologize. Okay. So 25 plus g equals to 20 root x, and if we square both sides, we'll have 25 plus g whole squared equals to 20 squared is 400 times of x. So therefore x equals to 25 plus g squared all over 400. And that should be our final answer, and this should be a merit level question. To get an achieve should be pretty much if you can square both sides one time. So if you can get up to this step here, you should get an achieved. Question D. Write k plus ki over 1 minus I plus 2k over 1 plus I in the simplest possible form. So for these questions, we might as well just work with each of them individually. So for k plus ki, we can multiply by the conjugate, which is multiplied by 1 plus I over 1 plus I, and then we'll have k plus ki times of plus of ki minus k all over 1 minus I times 1 plus I, so that would be all over 2. Okay, for 2k over 1 plus I, we can multiply the conjugate, so 1 minus I over 1 minus I. This will give us 2k minus 2ki all over 2. Alright, so in this case, we'll have 2ki over 2 plus 2k minus 2ki over 2. So if we simplify this a little bit, we'll have ki plus k minus ki. So therefore, ki and ki will cancel each other out, and this will give us just an answer of k. So that's our simplest possible form for this question, and this should be another it should be another merit level question here. To get an achieved grade, if you can multiply by the conjugate, so probably so multiply by the conjugate here, multiply by the conjugate there, you should be able to get an achieved. So question E, given that t equals to a minus bi over a plus bi, where a and b are real constants, prove that 1 plus t squared over 2t equals to a squared minus b squared over ax squared plus b squared. So for this question, it's actually, I found out it's a good idea to not try to rationalize anything too early, so just to keep it unrationalized for a time being. So I like to find an expression for 1 plus t squared and then find an expression for 2t. So we just find an expression for 1 plus t squared first. So we know that t squared equals to a minus bi squared over a plus bi squared plus 1. And if we want to make this into just one fraction, okay, so we can just say t squared plus 1 equals to so that's actually 1 plus t squared. Okay, so a minus bi squared over a plus bi squared plus a plus bi squared over a plus bi squared. And this should give us a minus bi squared plus a plus bi squared all over a plus bi squared. So that's our expression for 1 plus t squared. For 2t, we're going to have just 2 times of a minus bi over a plus bi. But since we're multiplying by 1 over 2t, so we're going to have 1 over 2t equals to a plus bi all over 2 times a minus bi. Alright, so now we're going to simplify this expression. So we have a minus bi squared plus a plus bi squared over a plus bi squared multiplied by a plus bi over 2 times of a minus bi. So in this case, we can cancel this one with 1 squared there. And okay, so now we have a minus bi whole squared plus a plus bi squared all over a plus bi times 2 times a minus bi. Alright, so now we're going to simplify this top part here by expanding out the brackets. So we have a squared minus 2abi minus b squared. And we're going to add on a plus bi squared, which is adding on a squared plus 2abi minus b squared. All over 2 times of, if we expand these brackets out, we'll have a times a is a squared. A times negative bi is negative abi. A times positive bi is positive abi. They will cancel each other out. Negative bi times bi is plus b squared. Alright, and now if we simplify this a little bit more, we'll see that this will cancel each other out there. And we have 2a squared minus 2b squared all over 2 times of a squared plus b squared. We'll cancel out these 2's here. So then we'll have a squared minus b squared all over a squared plus b squared, which is as required. Okay, so QED there. We're done with this question as required. And this should be an excellence level grade. In terms of getting a merit level grade, if you can show a manipulation, so in terms of getting somewhere up to this step here, that should be enough for a merit. To get an achieved, if you can find an expression for 1 plus di or just 1 over 2i, so probably just one of these two should be enough for an achieved. Question 2. Given that x minus 2 is a factor of 2x cubed plus 2qx squared minus 17x minus 10, find the value of q. Alright, so for this question, we're going to be using our remainder theorem. Okay, so we know that x minus 2 is a factor. That means if we plug in x equals to 2 into this cubic equation, we should be getting 0 as our result. Okay, so x minus 2 is a factor, so therefore, if we call p of x, so let p of x equal to 2x cubed plus qx squared minus 17x minus 10. So therefore p of 2 equals to 0. That's what we know. So therefore 0 equals to 2 times 2 cubed plus q times of 2 squared minus 17 times 2 minus 10. Alright, so just leave a little bit of calculated work here. So we have 2 cubed is 8, so 0 equals to 16 plus 4q minus 34 minus 10. So 16. So we should be getting that 28 equals to 4q, and therefore dividing on 4 on both sides, we'll see q equals to 7. And that should be our final answer for this question, and this should be an achieved level question. Find all the possible values of k given that the modulus of 5 plus 3ki equals to 13. So the modulus of 5 plus 3ki can be given by the square root of 5 squared plus 3k squared. So this is because, for example, if we have our Gantt diagram here, so let's say this is position of 5 plus 3ki. This is a complex number, z equals to 5 plus 3ki squared. The modulus is just the distance from the origin to the position of the complex number on the Gantt diagram. And since this length is given by x here and y here, so it's given by the square root of x squared plus y squared. That's our modulus of z, where x is our real part and y is our imaginary part. So in this case, our real part is 5 and our imaginary part is 3k. So that's our modulus is going to be square root of 5 squared plus 3k squared. And we know this equals to 13. Alright, so if we square both sides, we'll see that 5 squared plus 9k squared equals to 169. So 169 minus 25. So we should find that 144 equals to 9k squared. So we should be getting that k squared equals to 16, and therefore k equals to plus or minus 4. Okay, so plus or minus 4 should be our final answer for this question. This should just be another achieved question there. One of the solutions for the equation 2z cubed minus 15z squared plus bz minus 30 equals to 0 is z equals to 3 plus I. B is a real number. Find the other solutions and the value of b. So in this case, if we apply the knowledge of our conjugate root theorem, we know that if z equals to 3 plus I is a solution, we also know that z equals to 3 minus I is a solution. Right, so we can draw our first solutions here. So we have z minus 3 plus I multiplied by z minus 3 minus I. So these are our two solutions. And our last solution can be 2z plus c. The reason I have 2z here is because the coefficient of z cubed is 2. So I want to have that 2 in our last bracket there. So we're going to expand these ones out. So first we're going to simplify. So z minus 3 minus I times z minus 3 plus I times 2z plus c. Alright, so if we expand these two brackets out here, we have z squared. So indeed, when you're expanding these brackets with the conjugate, you can just ignore all the imaginary parts because they're going to cancel each other out because we're multiplying by conjugates here. So since all the imaginary parts are going to cancel each other out, any term with any term with an imaginary part, it can just be ignored. So z times z is z squared. Z times negative 3 is negative 3z. Z times I is zi. We're going to ignore that. So 3 times minus 3z. Negative 3 times negative 3 is plus 9. Negative 3 times I is 3i, we're going to ignore that. Z times negative I is negative zi, we're going to ignore that. And negative I times negative 3 is 3i, we're going to ignore that. Negative I times I is negative I squared, which is plus 1. And that's going to be multiplied by 2z plus c. So we're going to add up the like terms here. So z squared minus 6z plus 10 times 2z plus c. I'm going to expand this one out again. Okay, so we have 2z plus 3, so we're going to end up with 2z cubed plus cz squared minus 12z squared plus, minus 6cz plus 20z plus 10c. So for this case, we're going to see that 10c is the only term that's independent of x. It doesn't have a, not x, it's the only term that's independent of z. So therefore, 10c must be equal to the term that's independent of z in our equation, which is -30. And therefore, we can see that c equals to -3. So therefore, we can start to draw out our cubic, which is 2z cubed minus 3z squared minus 12z squared minus 6 times of -3 times z plus 20z minus 30. So if we add the like terms here, so 2z cubed minus 15z squared plus 18z, which is plus 20z, so that's plus 38z minus 30. So now we can see that clearly that b equals to 38. We know that the solutions would be, so the solutions are 3 plus I, 3 minus I. And we also know that the last solution is when c equals to -3. So that means 2z minus 3 equals to 0. 2z equals to 3. Therefore, 2z equals to 3. Therefore, z equals to 3 over 2. So that's our final real solution. So the solutions are 3 plus I, 3 minus I, and 3 over 2. Alright, and that is a merit level question like it is every year. If you can get the final answer, it's a merit. To get an achieved, if you can find the b value, or the third solution, either or, you'll get an achieved. Given that u equals to p plus pi and b equals to -q plus qi, p and q are both positive real constants, find the argument of u over v. So first things first, we've got to find a simplified equation for u over v. So u over v equals to p plus pi all over -q plus qi. Okay, so first we're going to be multiplying by the conjugates here. So we're going to multiply by -q minus qi, -q minus qi there. So we're going to have -pq minus pqi. So we have -pq minus pqi plus, minus pqi. So minus pqi. And pi times qi is -pqi squared, which is plus pq. All over q squared. Q squared here, and q squared plus q squared again, because that's 2q squared there. Alright, so if we simplify this a little bit, okay, this equals 2. So we have -pq and pq cancel each other out. So we have -2pq over 2q squared I. U over v equals to -2p over 2q. By the looks of it, so I. Alright, so the thing we know that p is greater than 0, and we all know q is greater than 0. So therefore we know that -2p over 2q must be less than 0 because of this -2 coefficient. So since this is less than 0, and this is also an imaginary term, we can actually look at this on our Gann diagram as this position here. So we have -2p over 2q. Actually, that can be simplified to just -p over q, to be honest. So -p over q. Okay. So that's our imaginary part here. This is our real part here. Since we know that the real part is equal to 0, since they cancel each other out, this imaginary number is purely imaginary and it's negative, meaning that it's located along the negative end of the imaginary part of the spectrum, and therefore our argument would be equal to this angle here, which is -pi over 2. So argument of u over v therefore equals to -pi over 2. This should be another merit level question. To get an achieved, you can correctly multiply by the conjugate and get an expression for u over v. So up to here, you should get an achieved. Question E, find the Cartesian equation of the locus described by conjugate of z plus I squared plus conjugate of z minus I squared equals to 10. Alright, so first things first, we've got to define z. So z is a complex number, any complex number. So we'll say let z equal to x plus iy. So we're going to have x plus iy plus I plus of x plus iy minus I that equals to 10. So if we have x plus of, if we group the like terms, so y plus 1i plus of x plus y minus 1 times of I, that equals to 10. And this is all squared, okay, so apologize. So everything's squared, so therefore we have square root of x squared plus y plus 1 squared, and this is squared, plus of x plus y minus 1 squared, x squared. So x squared plus y minus 1 squared, whole thing squared equals to 10. Okay, so there we go. So we have x squared plus of y squared plus 2y plus 1 plus of x squared plus y squared minus 2y plus 1, that equals to 10. So we have here that our 2y and negative 2y cancel each other out. X squared plus y squared equals to, I apologize. So x squared plus x squared is 2x squared. Y squared plus y squared is 2y squared. 1 plus 1 is 2. At least I think so. But 1 plus 1 is 2. That equals to 10. Alright, so 2x squared plus 2y squared equals to 8 if we subtract 2 on both sides. 2x squared plus y squared, if we divide on 2 on both sides, will give us 4. So that is in this equation, x squared plus y squared equals to 4. We can give a little bit of a description. You don't have to, but it's good if you can. So we can say this represents a circle with radius 2 and center of 0, 0. Alright, and that's the end of this question, and this should be an excellence level question, okay? To get a merit level grade, I think we should be looking at getting up to the point where you can write this equation here. So if you squared both sides and you're trying to cancel everything out, that should be a merit. To get an achieved, if you can write it in terms of this step here, so you can group the like terms and then let z be equal to x plus iy, should get an achieved. Alright, so let's have a look at question 3. If u equals to 12k cubed cis pi and v equals to 2k cis pi over 3, find the exact value of u over v in polar form. Alright, so u over v, we can see it's 12k cubed cis pi over 2k cis of pi over 3. So in this case, the angle is subtracted. If we divide, the angle is subtracted and the lengths are divided. Okay, so in this case, we have 12k cubed over 2k, that is 6k squared. And we have cis of pi minus pi over 3, which equals to 6k cubed cis of 2 pi over 3. And that should be an achieved question there. Question B, if z equals to 5 minus I and w equals to negative 2 plus 3i, show that the modulus of z squared equals to 2 times the modulus of w squared. So the modulus of z is equal to basically the length of the distance to a complex number, which in this case we should have it somewhere here. So this length L is our modulus, so we should be getting it by 5 squared plus 1 squared. Well, technically it's negative 1 squared, but that's just going to give us a positive. So it's the same as saying 5 plus 1 squared. So this should give us a square root of 26. That's the modulus of z. And the modulus of w is equal to square root of 2 squared plus 3 squared, which is equal to square root of 3 squared is 9, 2 squared is 4. So that's square root of 13. And we know that the modulus of z squared equals to 26, and the modulus of w squared equals to 13. And therefore, we can say that the modulus of z squared equals to 2 times the modulus of w squared. And that should be another achieved question there. Given that z equals to a plus bi, and a and b are non-zero real numbers, show that z times the conjugate of z over z plus the conjugate of z is a real number. So first things first, we've got to say that the conjugate of z must be equal to a minus bi, so that's the first thing we got to define. On the numerator, we have a plus bi multiplied by a minus bi. On the denominator, we have a plus bi plus a minus bi. So therefore, if we simplify this a little bit, we'll get a squared plus b squared all over. So this then will cancel each other out, and we have a plus a, which is 2a. So very simple question there. So you can say that since a squared plus b squared over 2a is purely purely real, hence this is a real number basically. And that should be our final answer for this question. Okay, a pretty simple question. This could actually just be an achieved question, I'm not too sure. But perhaps they might do it the way maybe they can give you an achieve for getting this up to here. And if you add the explanation, they might get you a merit. Yeah, I'm not too sure how they're going to mark this question. It seems pretty straightforward. But for question D, we have z to the power 4 equals to negative 16k to the power 8. K is a real constant. Give your answers in polar form in terms of k. Right, so first things first, these questions, I like to put this on the Argand diagram first to get a clear picture of what I'm dealing with. So first things first, just draw a rough sketch, doesn't have to look pretty. So we know k is a real constant. So therefore, since k is a real constant, any constant to the power of an even power is going to be positive. K to the power of 8 is positive. So negative 16 k to the power of 8 must be negative. And since this is a real, this is completely real, there's no I or anything, so this is a real number. And we know it's negative, so therefore it has to be on the negative side of the real spectrum. So our z to the power 4 will be located somewhere here. So that's our z to the power 4 equals to negative 16 k to the power of 8. So we can write this in terms of our polar form. Okay, so that's our z to the power 4 equals to the modulus, which is just 16k8. That's the length from here to here. It's not negative 16k to the power of 8 because we're looking at the modulus. Okay, the modulus is the length, and length is not considered to be negative. So the length is just purely 18k to the power of 8. And our angle is from our positive spectrum here. So that's going to be our angle. That's going to be theta. And we know that that's going to be equal to pi. Okay, so that's pi. Since a whole revolution is 2 pi radians, so half is going to be just pi. And now we're going to say we're going to take the fourth root on both sides. So the fourth root of 16k8 will be 2k squared. And the power will be divided by 4, so this becomes pi over 4. That's our first solution. Our second solution would be the same modulus here, so 2k squared, that doesn't change, but the location of the complex number on the Argand diagram will change, and the reason this changes is because of the angle. So since this is z to the power of 4, so the way you can remember it is that a full circle, so full revolution, is equal to 2 pi. So therefore, since this is split, so there's 4 solutions in total, since it's z to the power of 4, it's the 4th order, so there's 4 solutions. So therefore, there's going to be 4 possible solutions around this whole revolution. So therefore, each solution will exist, so partial will exist at each 2 pi over 4 interval. So we can say that pi over 4 plus 2 pi over 4. So this equals to 2k squared cis of 3 pi over 4. Z cubed, the third possible solution is same modulus, so 2k squared, cis of 3 pi over 4 plus 2 pi over 4. This equals to 2k squared cis of 5 pi over 4. And you can change it to a negative if you want, but you don't have to. So if you change it to a negative, you will get negative 3 pi over 4. The fourth solution is 2k squared cis of negative 3 pi over 4 plus 2 pi over 4. This equals to 2k squared cis of negative pi over 4. And that's our final answer for this question. Okay, we're done with this question. If you can get all 4 solutions, you'll get a merit grade. If you can get an achieved, it's probably just being able to find one solution. If you can get up to this step, you'll get an achieved. For complex numbers u and v, prove that if the modulus of u plus v equals to the modulus of u minus v, then u over v must be purely imaginary. First things first, we've got to define our complex numbers. Okay, so we're going to say let u equals to x plus iy. Doesn't matter what letters you use. Okay, I like using x plus iy and a plus bi. It's easy to distinguish. If I can write it down properly, so x plus iy. And we can say that v equals to a plus bi. Okay, you can do any letter you want. It can be like m plus ni. It doesn't really matter. Okay, just define your variables. I like using x plus iy, and I like using a plus bi. That's just a personal preference. But if you would rather use like c plus zi, it doesn't really matter. Okay, so we have our u plus v, which is x plus iy plus a plus bi equals to modulus of x plus iy minus a minus bi. So therefore, if we simplify, so we have x plus a, we're going to group the real parts together, and we're going to group the imaginary parts together. That equals to the modulus of x minus a plus y minus bi. So therefore, square root of x plus a squared plus y plus b squared, that equals to square root of x minus a squared plus y minus b squared. If we square both sides, we'll see x plus a squared, x plus a squared plus y plus b squared. That equals to x minus a squared plus y minus b squared. If we simplify this a little bit, we'll have x squared plus 2ax plus a squared plus y squared plus b squared plus 2yb. That equals to everything on the right hand side, which is x squared minus 2ax plus a squared plus y squared minus 2yb plus b squared. So we can see that certain terms will cancel each other out. So x squared, a squared, y squared, and b squared will cancel each other out. We'll have 4yb equals to negative 4ax, yb equals to negative ax. Okay, we'll just leave it there for now. We'll remember this. So yb equals to negative ax. Yeah, okay, so now we're going to look at u over v. So u over v would be x plus iy over a plus bi. And if we multiply by the conjugate here, we'll make our lives easier. So a minus bi over a minus bi. This will give us x plus iy times a minus bi all over a squared plus b squared. So u over v equals to, we're going to expand the brackets. So ax minus bxi plus ayi minus ybi squared, which is plus yb. So therefore, this is all over a squared plus b squared. We're going to separate this into our real terms and our imaginary terms. So u over v equals to ax plus yb over a squared plus b squared plus of ay minus bx over a squared plus b squared I. But now we know we're going to come back to here. We're going to say that yb equals to negative ax. Yb equals to negative ax. So we can substitute that one in. We can substitute yb equals to negative ax. So u over v equals to ax minus ax all over a squared plus b squared plus of ay minus bx over a squared plus b squared I. This will just give us ay minus bx over a squared plus b squared I. So we can say that since the real part of u over v equals to 0, u over v must be purely imaginary. And that's our final answer for this question, okay? And that's finished. That was actually a pretty long question, pretty difficult, but if you can finish everything here, you'll get an excellent grade. To get a merit grade, if you can just prove one of these, like if you can get up to this step here, or if you can get up to this step here, that might get you a merit, to either or. To get an achieved, if you can just show some manipulation, maybe multiplying by the conjugate here, getting and separating out your variables, that might get you an achieved. Maybe getting up to this step here, that might get you an achieved. Alright, so thank you for watching this video. I hope you enjoyed, and I see you all in the next one.